Hello everybody, my name is Kenneth Butcher, and today I'm here to answer the big question in everyone's mind. Where does it land? So, to start off with, I just want to look at this little position graph we have here. It's a crude and very mental image of this position function, r of t, and as you can see, the object goes up and it comes down. My job is to find where this position right here is. So one thing that I immediately notice when I'm looking at this graph is that the y value of this position is equal to 0. So if we look back at our RT functions, there is a clear x half, and y component. So because y equals 0, we can just completely and utterly forget about that y component, including one of the things we'll be forgetting is this a. This a we will forget all about it for the rest of today's discussion. Now, all that leaves us with is this here x component. And since this r of t can just be renamed as d for now, for like the distance it travels. Now, one of the things we were given is that little t is equal to negative big T. So if you see in this equation, what I've done is I've replaced all the little t's with big T's. So we have one variable that describes the amount of time that the object is in the air. Now, in order to find a better justification for this distance, I need to know how long the object is in the air. So to do that, I'm going to take this equation and solve for big T. Now, when I did that earlier, it took a long time and was very difficult and used a lot more whiteboard room than this. So for today, I'll just hope you guys trust me when I say that the amount of time the object was in the air is equal to this. Now that looks all good and well. We now know where or how long in seconds the amount that the object will be in the air. But that's not the question. We want to know where does it land. We want to know this here d. So we're just going to do a couple quick calculations. We're going to get rid of that square root first. We are going to take out the 3/2. So that t squared over 3/2 is equal to d over b. And that gives us our final answer, that the distance is equal to the constant b times the amount of time squared over 3/2. Now, the two big variables here are going to be time in the air and distance, since b is a constant, 3/2 is a number. As you can see in this equation here, as time increases, so the more time that the helicopter will spend in the air, the greater distance, the greater the number of distance will be in the end. This makes a lot of sense, as the longer an object spends in the air, the more distance it tends to travel. Thank you.
So today, my name is Jack Large, and I will be explaining the motion of this helicopter. So, to start with, we were given an acceleration function, and through the video, we know that down the tree of integration, we end up with this position function here. Now, we know that plugging in big T gets us these two, but why plug in big T? We know that the helicopter travels from negative T to T, and that total distance that it covers is d. Displacement is d. So this is going to be d over 2, because big T and little t are both equidistant from this y-axis here. So we know that this distance and this distance are equal, which is why we're able to claim that this position is d over 2. So the change in x, this is how far the helicopter moves in the x-axis direction. Now, where does this 2 beta t squared over 3 come from? That is where we plugged in t. Now, through this, plugging in t, canceling out, plugging in t, canceling out, this is the total distance traveled in terms of time. Now, for delta y, it's much of the same thing, only with alpha instead of beta, and we end up with 2 alpha t squared over 105. But what does that mean? This is the helicopter's total change in the y direction, and this is the helicopter's total change in the x direction. So how long was it in the air if both of these are dependent on t? This t equals root 3 over 2 times d over beta is how long the helicopter was in the air the total time. And that comes, there are multiple ways to solve for t. You could solve it from this equation, or even from the position function as a whole. Kenneth solved it through this RT to prove what big T was, the total time. This delta R here is basically just showing what the change in X and the change in Y are in one concise equation. And the change in time is going to be this negative big T to positive big T. So, or because these are the same distance, just 2T. And to get it out of terms of T, just to be more understandable, if you will, that's just going to be 2 root 3D over 2 beta.
Hi, I'm Alexa, and today I will be doing the reflect and reasoning section of this project. Now, in this project, we are measuring the horizontal displacement of the helicopter as well as time it takes. And for the reflecting portion of this segment, I will be comparing this problem to a similar problem we have done in the past. This problem is homework on homework number 3, and it is problems 1 and 2. The reason why I chose to do both of these problems is because they are using like the same example pretty much. And what I mean by that is on question 1, you are asked to find the height of a cliff. So let me just draw that real quick. So you're asked to find the height. There we go. Of a cliff. And you're given initial velocity as well as you're given theta. The reason why I chose this problem is because the ball, which is what helps you find the distance it's being thrown, actually behaves in a way, like the movement behaves in a way where it's similar to a parabola. Cliff. And this is similar to how our helicopter also moves in a parabola motion, where it goes from negative t to t. All right, and then the differences in these two problems is in the helicopter, we are measuring the, like I said earlier, the horizontal displacement in between negative t and t. However, in this problem, we are measuring the vertical displacement of the ball's distance, pretty much. To further, I guess I should have said this earlier. To further elaborate on what I mean by the parabola shape is in part 2 or question 2 of the homework. I am referencing, you are asked to throw the ball back. And so in that way, we are able to make the connection that they are parabola. That's what I meant to add. All right. Another difference is the rock actually stops in its motion, because in problem 1, you're asked to find the hill's height in reference to when it stops on top of the hill. And then in problem 2, you're asked to find the displacement when it is thrown back. However, in the helicopter problem, the motion never stops. It doesn't stop at anywhere in between these 2 points. It is continuous. And finally, in the hill or cliff problem, you're given theta. And that is essential for helping you find this distance. However, as you can tell, there is no theta anywhere in this work. So our answer of distance and horizontal displacement is not dependent on an angle measurement. All right, thank you.